Section 6.5 is solving square roots and radical equations. I can solve square root and other radical equations. Big ideas for this section. Solving a square root equation may require squaring each side of the equation. This can introduce extraneous solutions. A radical equation can be solved by isolating the radical on one side of the equation, then raising each side to the power suggested by the index. And the nth root of an expression that contains an nth power as a factor can be simplified. A radical equation is an equation that has a variable in a radicand or a variable with a rational exponent. Guys, there we just mean fractional exponent. If the radical has an index of 2, the equation is called a square root equation. If the index is 3, it's a cubed root equation. If the index is 5, it's a fifth root equation. It just depends on what that index is, but we're going to solve them all with the same type of pattern. So in example 1, we're going to solve a square root equation. So just like we did with quadratics and with absolute value, before we can get inside the square root there, we have to have it all the way by itself. So our first step is going to be to get rid of this 3. And now it's a positive 3, so we get rid of it by subtracting. Now the only thing I have left on the left side is the square root of 2x minus 3. We're going to get rid of that square root by using its inverse. And we talk about inverse operations when we were first solving equations. The inverse operation of addition is subtraction. The inverse multiplication of dividing is multiplying. And we'd get rid of a squared by taking the square root. We can do the same thing to get rid of a square root. If we square both sides, okay, again, whatever we do to one side, we have to do to both. It accomplishes a similar process here. What we really have is 2x minus 3. Radicand becomes our base. Our exponent goes to the numerator. And our index goes to our denominator. So we have 2x minus 3 to the first power, which is just 2x minus 3. So because our index and our exponent are the same, it's like they cancel each other out. They divide out to be just a 1, and we have just 2x minus 3. And again, whatever we do to one side, we have to do to both. Now we can solve from here just like we have been all year, like we did in Algebra 1, like we've been doing forever by getting our x by itself. So add 3 to get rid of a minus 3. And divide by 2 to get x by itself. We should double check, plug it back in to make sure. 2 times 14 is 28, minus 3, 25. Take our square root. We get 5 plus 3 gives me 8. So it checks, and we are good to go there. Now, feel free to pause here and give this a try if you'd like. What is the solution of the square root of 4x plus 1 minus 5 equals 0? So again, our first step is to try and get our square root by itself. In order to do that, I have to get rid of this minus 5, and I'm going to add 5. Again, we're talking inverse operations to get it to be 0, because we don't want anything else on the same side of our square root except for our square root. Now, to get rid of the square root, we are going to square both sides, because as long as our exponent and our index match, they cancel out to just be 1, and anything to the first power is just itself. 5 squared here gives me 25. Now we solve just like any other equation. So I subtract 1 and divide by 4. X equals 6. Let's double check. 4 times 6 is 24 plus 1, 25. Take the square root. 5 minus 5 is 0. So it checks. Perfect. In example 2, we have other radical equations, and we're going to solve these very similarly. There's a little bit of a difference in the middle in that there's just an extra step or two, but not the end of the world. It's just a couple more things, not super difficult, and we can handle this. So right now we're still going to try and get, here it's an exponential form, but it's still a radical equation. So we're going to get that by itself by dividing by 3. And that set it equal to 4. You don't have to here, but I think it's a little bit easier personally, and in past years, a lot of the students have thought it was easier to switch it to radical form here so we can really see what we're doing. If you feel comfortable with using these rational exponents, go for it. We raise it to the 3/2 power so that when we multiply we get 1. But what I'm going to do instead is from here, I'm going to put it into radical form. My base becomes my radicand. My numerator becomes my exponent. And my denominator becomes my index. Now, that was one of our different steps. Now, instead of just getting rid of the radical, we also have to get rid of our exponent. And it doesn't matter what order we do this in. If we get rid of our exponent first, though, it keeps our numbers smaller, easier to work with, more mental math friendly, and just kind of helps us see what we're working with a little bit better. So that's usually what I lean to, but you can really do either one of them. It doesn't matter from here. So to get rid of a square, we're going to take the square root of both sides. And we've done that before for a while here. So to get rid of a square, I'm going to take a square root. And again, as long as those match, they cancel each other out. So what I'm left with is the cubed root of x plus 1 equals. And when we introduce a square root here, guys, that means that we don't know how we got to 4. It could have been positive 2. It could have been negative 2. So we need the plus or the minus there. Okay, now to get rid of the cubed root, just like we did in the last example, we are going to cube both sides. As long as those match, they cancel. And we have x plus 1 equals plus or minus 8. Guys, one thing to think about here, guys, is it's not always going to be plus or minus. It depends on what type of a root we took. So since we took an even root, a square root, a fourth root, an eighth root, a hundredth root, whatever you end up taking there, we're going to get plus or minus. But if it was an odd root, like 3 or 5 or 9, it would just be the value itself. Okay, so we'd either get negative 2 or positive 2. But when it's even, we don't know what we started with to get us to 4. Could have been negative 2 times negative 2 or positive 2 times positive 2. So we need that plus or minus. So anytime our numerator is even, okay, that's really what we're looking for. Now, last step is to subtract 1. And when we do this, we need to be careful. We take positive 8 minus 1 to give me 7. And negative 8 minus 1 to give me negative 9. It's not just plus or minus 7, so be careful there. We have to treat it as two separate pieces, a positive 8 minus 1 and a negative 8 minus 1. Let's double check here. 7 plus 1, 8, raised to the 2/3 power 4 times 3 is 12. Negative 9 plus 1 is negative 8, raised to the 2/3 power 4 times 3 equals 12. So both of these work here. Same idea here with b. We're going to try and get our radical by itself. So I'm going to subtract 1 first of all. And then I'm going to divide by 3. Okay. Now we have two options. We can get rid of our 5th root first by taking it to the 5th power, or we can get rid of our cubed first by taking the cubed root. If we get rid of our 5th first, which we certainly can do, but we're going to have to take 8 to the 5th power, which is going to give us a huge number that we're not going to want to really have to break down very easy. But if I take my cubed here and get rid of it by doing the cubed root and take the cubed root of 8, I just get 2. And that's going to be a whole lot easier to work with here. And this doesn't have to be in parentheses anymore if you don't want them. That 2 is going to be a whole lot easier to work with than it would have been if we'd have gotten rid of the 5 first as the 5th root. Again, either way will get you to the right answer, but if we can deal with smaller numbers, we might as well work a little smarter, not harder there. So now to get rid of our 5th root, we take the 5th power. So the big idea here, guys, is that we're going to have each one of them to be a complete set. So an exponent and an index. an exponent, and an index, because that's going to cancel and give us just 1, and anything to the first power is itself. 2 to the 5th power here is 32. Then I can subtract 1 and get 31. When I plug it in, 31 plus 1, 32, 5th root, 2 cubed 8 times 3, 24, plus 1, 25, and that checks. So we are good to go there. Go ahead and pause here and give this a try if you'd like. First step is to get our exponential function there, exponential part of our function, factor there by itself, and we do that by dividing. X plus 3 raised to the 2/3 power equals 4. Again, we have two options here. We can work with this as an exponent if we want to by raising it to its inverse, its reciprocal, or we can switch it to radical form, and that's the way that I'm going to go. Our base becomes our radicand, our exponent becomes our numerator, and our index comes from our denominator. Now this shows me a little bit easier what things I need to do with these values. So I have a 2 and a 3 here, and that's great, but by seeing it in radical form, that helps me remember which one I'm going to use as an exponent, which one I'm going to use as a root, and to kind of keep things a little bit more organized. So I'm going to get rid of my squared first by taking the square root. And since it's an even root, it's plus or minus 2. I can get to 4 by taking 2 times 2 or by negative 2 times negative 2. Next, we're going to get rid of a cubed root by cubing both sides. And I have x plus 3 equals plus or minus 8. We subtract 3 to get our x by itself, and then again, remember here, 8 minus 3 is 5, and negative 8 minus 3 is negative 11. And if you plug those in, they both check. In example 3 here on page 392, it says, for meteor crater in Arizona, the formula d equals 2 times the cube root of v divided by 0.3 relates the diameter of the rim in meters to the volume v in cubic meters. What is the volume of meteor crater? Keep in mind all values are approximate here. So if we look at the picture in the book, it tells me that my diameter is 1.2 kilometers, but we needed our diameter to be in terms of meters. So we're going to multiply by 1,000. Kilo means 1,000. So what this is really telling us is 1,000 meters. And my diameter is going to be 1,200 meters. Now that I know my diameter, I can plug that in for diameter and solve for v. First thing I'm going to do is divide. And now, to get rid of my cubed root, I'm going to take it to the 3rd power. I'm going to cube it. So those cancel, and whatever we do to one side, we have got to do to both. Now that my radical's gone, I can multiply both sides to get where I need to be, which is with my v by itself. And my label here is meters cubed. Now, suppose the diameter of a similarly shaped crater is 1 kilometer. What is the volume? And again, we're going to use the same formula here of d equals 2 times the cubed root of v divided by 0.3. My diameter is 1 kilometer here, which means 1 kilometer, which is 1,000 meters. So my diameter is going to be 1,000 meters, and I need it in terms of meters to plug it into my formula. So I have 1,000 equals 2 times the cubed root of v divided by 0.3. Now we're going to get our radical by itself by dividing. To get rid of my cubed root, I cube both sides. Again, as long as our index and our exponents match, those cancel out. Here, I'm going to have 125 million equals v divided by 0.3. So I multiply to get rid of my division, and I get 37.5 million meters cubed for my volume. And that's all I have for the first half of section 6.5.